a narrow beam of protons and neutrons, each having the same momentum, enters a region of uniform magnetic field perpendicular to their direction of momentum. What would be the ratio of the radii of the circular path described by them? So here protons and neutrons, they are traveling with the same momentum, and the magnetic field is perpendicular to their direction of momentum. It means that this magnetic field is perpendicular to their velocity, to the direction of velocity. So the direction of magnetic field will be perpendicular to their direction of motion also. Now what happens if a force is acting perpendicular to the direction of motion of the particles? Then we know that will provide the centripetal force. That is the centripetal force, the nature of centripetal force. We know that when a charge q is moving with a velocity v in a magnetic field B, magnetic field of intensity B, that charged particle will experience a force. Actually force is equal to q into v cross b, q will be sine theta, and when the charged particle is moving perpendicular to the magnetic field, then v cross b will become vb sine 90. So the maximum force will be experienced, and then the force will be acting perpendicular to the direction of velocity, to the direction of motion of the particle. So we know that will provide centripetal force. So this force qvb, that is equal to centripetal force mv square by r. So the radius can be calculated, the expression for the radius. So we have momentum in the numerator and divided by the product of charge and the field. Now here we know we have proton and deuteron. Here in the question it is given that protons and deuterons are moving perpendicular to the given magnetic field with the same momentum. So suppose we are considering protons. Proton, we know that is the nucleus of first isotope of hydrogen. We can consider like that. So we know the nucleus of hydrogen atom. So we have one proton. So what is the charge? Suppose we are saying that q is the charge of proton, q. Then suppose we are considering deuteron. Deuteron, we know that is the nucleus of deuterium. So in its nucleus it will be having one proton, and in addition to one proton, one neutron also. Neutron. But we know this neutron is neutral. Neutron is neutral. So what is the charge? Charge of deuteron? That is the charge of proton. Charge of deuteron is equal to charge of proton itself, because neutron is chargeless. So we are able to find that charge of proton, and that will be equal to the charge of deuteron. That is a relation of their charges. Charge of proton is equal to charge of deuteron. And in the numerator we have momentum, and in the question it is given that both particles are having the same momentum. So numerator remains the same, and both are moving in the same magnetic field, so b value also remaining the same. Now we have seen that the charge of proton is equal to charge of deuteron. So they have the same magnitude, means the radius of the path described by proton and deuteron in the same magnetic field with the same momentum, if they are entering the field perpendicularly, the radius, they have the same magnitude, their radii have the same magnitude. So their ratio is equal to 1:1. Two particles A and B of masses m and 2m, mass of second particle is double that of first, have charges q and 2q. Charge of second particle is twice that of the first. Both these particles moving with velocities v1 and v2 in the same direction enter the same magnetic field acting perpendicular to their direction of motion. If force on first particle, that is Fa, and force on second particle, that is Fb, they are acting in the ratio 1:2, then find the ratio of their velocities. So here we know that F is equal to Q into V cross B, Q will be sin theta. And force experienced on first particle, Fa, Q, the charge of first, V1, the velocity of first particle, P sin 90, because these particles are entering at an angle 90 degree with the magnetic field. Now the force on, so the charge of second particle is double that of the first, V2, the velocity of second, B sin 90, both are entering to the same magnetic field. So this ratio is given as 1:2 in the question, Fa by Fb, that is 1:2. So 1/2, that is equal to, here Q will be cancelled, Q will be cancelled, B will be cancelled, and sin 90 also will be cancelled. So what else remaining? Here the ratio is 1/2, that is equal to V1 by V2 into 1/2. Q will be cancelling, then that 1/2 factor is coming there. So half is equal to half into V1 by V2. So what should be V1 by V2? 1:1. A beam of alpha particles projected along the positive direction of x-axis experience a force due to magnetic field along the positive direction of y-axis. What is the direction of the magnetic field? This question can be solved either by applying Fleming's left-hand rule or by analyzing the vector product of V and B, V cross B. According to Fleming's left-hand rule, we know that the three fingers of left hand, thumb, middle finger, and the pointer finger should be aligned in three mutually perpendicular directions, and pointing finger points the direction of magnetic field, thumb represents the direction of force, and the middle finger represents the direction of current. So here in the question it is given that alpha particles, a beam of alpha particles projected along the positive x direction. So alpha particles, they having positive charges. So alpha particles are having positive charges. So the direction of motion of positive charges, it is the direction of motion of current itself. So if alpha particles are moving in the positive x direction, in this direction, then that will represent the direction of current also. So in the question it is given that these particles, alpha particles, experiences a force due to magnetic field along y-axis. So they experience a force due to magnetic field along y-axis. So force is denoted along y-axis. This is the direction of force. Force is denoted along y-axis. So Fleming's left-hand rule, three fingers of left hand, that is a thumb, pointing finger, and the middle finger should be aligned mutually perpendicular to each other, and this thumb represents the direction of force, and this middle finger represents the direction of current. So here it is given that alpha particles, that is positively charged particles, are moving along x direction. So that is the direction of current. So this middle finger is used to point the direction of current, and then the force is along y direction, positive y direction. So the thumb aligned along the positive y direction, and next comes the index finger, that is the pointing finger, this finger, and these three fingers should be held mutually perpendicular to each other. So mutually perpendicular to each other. Then this index finger is pointed into the plane of this whiteboard, into. So this index finger is used, this index finger, that is the pointing finger, is used to represent magnetic field. So here the magnetic field is pointed into the plane of this whiteboard. So into, so that is along z direction, specifically speaking that is along the negative z direction. Thumb for force, this middle finger for current, and then this pointing finger that is pointed into. So the magnetic field is given by the direction of magnetic field is given by the direction of index finger, pointing finger, that is pointed into the plane of the whiteboard. So the magnetic field is along negative z direction. The same answer can be obtained by analyzing the vector product. We know to analyze the cross product, vector product of two vectors, we need the help of cyclic coordinates I, j, k, and in this order, that is I cross j will be equal to k and k cross I will be equal to j. If the order is reversed, that is I cross k, then that will be equal to minus of j. And in the question it is given that force due to magnetic field is acting along y direction, that is force due to magnetic field, force, this force is acting along y direction, force is acting along y direction, it is given in the question. So the unit vector associated, that is j, so f, that is unit vector j cap is given, and the stream of particles, positively charged alpha particles, they are moving along x direction. So the unit vector associated with the velocity vector, that is I. Then what about the direction of magnetic field? What should be the unit vector associated with that? So here we are getting force along the y direction, unit vector is j, and I cross, what gives j, and here we know I cross k will be equal to minus of j, I cross k is equal to minus of j. So what about I cross minus k? I cross minus k will be equal to minus of I cross k, and I cross k is equal to minus j, so this will be equal to minus of minus j, that will be plus j. So the unit vector associated with b should be minus of k to get j here. So the unit vector associated with b, that is minus of k. So unit vector associated with the magnetic field vector is minus of k. Then we know that I cross k is equal to j, and I cross minus k will be equal to j. So we are able to find that again the magnetic field vector is acting along minus k direction. K is the unit vector associated with the positive direction of z axis. So minus k is the unit vector associated with the negative direction of z axis. So B should be pointed into the plane of this white board. So that is along minus z direction.